Okay, so I will summarize what we have obtained during the first session. So when you look at the model of in discrete time of open quantum system subject to decoherence and measurement back action, you have two ingredients. So you start from across a quantum channel. Okay, that could be decomposed as this. Here, Y is the index of measurement outcome. Okay, where each of this guy is a cross map, so complete preserving the complete positivity, but not the trace. And this guy is a quantum channel, so the trace is preserved too. Okay, how to obtain this from elementary things? It is something like this here. Your quantum channel, you can always express it in this form with operator mu, okay? So you have this kind of stuff. You have M1 rho, M1 dag, and here I have M mu rho, mu dag, okay? I put this in a kind of columns, okay? So this is, in fact, the way you can describe your quantum channel. Of course, this formulation is not unique, of course. And here, what you have is a stochastic matrix. So here you have 1, here you have the index mu, and so on. And here you have the index corresponding to Y. And here I have eta 1, 1, and the general thing I have eta Y mu. Okay? And this matrix is a stochastic matrix, left one. So here, when I take the sum of over Y of eta Y1, it is equal to the sum over Y of eta Y mu, it is equal to 1. So each sum of the columns. Okay? And then what you do to obtain ky, it is just a block multiplication of this. So here, what you obtain, k1 of rho, it is the sum, okay, over mu of eta 1 mu, okay, mu rho, mu dag, okay? It is typically something like this. You can always decompose this like this. Here, you can use a quantum, a cross map instead of that, okay? You can gather here, okay? Something like this. So but it is something like this, okay? And then what you have a Markov chain. According to this probability law, you detect yk, you choose the partial cross map k indexed by yk, okay, you divide by the trace, and the trace is the probability to detect y, k, knowing rho k, okay, everything is here. So it is, and one point is important, is that the probability to detect y is a linear function of rho. Yes?
Cardinality of the index mu is fixed, or it can change, like the decomposition is not unique, but
No, decomposition is not unique, so you have to do this based on the physics of your system. Okay?
like this mu dagger, mu is like a POVM.
Yes, in a certain sense, yes, in a certain sense.
So what I was asking was the number of mu's that are there.
Yes, number of mu's. In fact, at the end, what you have, this guy is intrinsic. But as you have the decomposition of K is not unique, of course, the decomposition of Ky like this is not unique, okay? It is this thing, but I will not enter into the detail into the gauge degree of freedom that you have in this, okay? In general, on example, you do not have any ambiguity on that, okay? But it is the rule is this. So which means that at the end, you have your quantum channel. You take part of your quantum channel, okay? Each part is, in fact, labeled by Y, okay? And you use this trick, okay? Just this. Okay, at the end. And now we will go to, in fact, continuous time, and with Wiener and Ito formulation. So I will take, for tutorial purposes, I will take the Rouchon experiment, okay? But in this case, I will reverse the role of the atoms M of a photon. I will assume that the photon will measure the atoms, okay? So I have to change a little bit the things. So I assume you remember, maybe I can go back for people who were not here, yes. So here are, in fact, the probe in the probe atoms. They get, I assume here that they get outside the box G, the wave function is psi, and here I assume that the interaction here is in fact resonant, and I obtain this evolution just before detection, and then we detect G or E. Okay. Now we will detect psi. Of course, we will detect this with we detect the position Q or the impulsion P. Okay. But I will change a little bit the initial state here. I don't want to use G, and I will fix the initial state for psi, and I will assume that I don't know the initial state for the qubit. Okay? So we reverse the things. So here is the thing. So what I have is psi now will be the state of a qubit. Okay? And here I use for, in fact, to simplify the computation, I use a coherent state, okay, which is slightly, in fact, displaced from 0, okay? Here you will see that you will get the Wiener approximation with alpha small, okay, in this case. With alpha small and also with theta small, both. You assume that you have these two parameters, and we will use theta and alpha small and do the asymptotic expansion and see that at the end, okay, we obtain the stochastic master equation, but driven by Wiener noise. Okay. So in this case, so I assume psi is the initial state of the qubit. Here it's the probe photon, and here I assume just dephasing, okay? Depending on the state of the qubit and on the state here, okay, like this. So it is not very difficult to see that this guy, it is just this, okay? And here you know that when you have this operator on the photon, it just turned, in fact, the amplitude, okay? When you applied exponential of E theta n is the photon number to a coherent state, you turn of an angle alpha of theta or minus theta here. So here you obtain this guy. And now what you have to measure something on your system. Of course, when I look at this representation here, the index y here is not discrete, but it is continuous, okay? Because I assume that I measure the Q position, okay? So I have a lot of possibility. It is continuous. So the outcome is a continuous label, not in a discrete one. So here is the measurement of Q, where A is the annihilation operator. And you can always, in fact, describe it as, in fact, the orthogonal, a sum of orthogonal projection on the Q value, okay? It is, with value Q, and with this thing. So, since you have this decomposition, of course, which is, in fact, the Q representation, okay, of, in fact, a coherent state. Okay? So a Q representation of a coherent state, here it is, since I use this, you have a shift, a Gaussian. You see the Gaussian coming from, in fact, the Wiener noise comes from here. The Gaussian is here. Okay? Here, alpha sinus theta, in fact, is just the shift. And here you have a phase, depending on Q. So, and then you will take this guy, and only this component. When you measure Q, you project this thing on the value, the eigenspace Q. So what you obtain, okay, is this thing. So when you applied, so this results Q on this, so you can inject this formula in this formula here, and you obtain a sum, okay, with respect to Q of this guy, okay? It is exactly the analog of Mg and Me that we obtain. Here I have Mq here, okay? You see? And then what we have, when we measure Q, we have, in fact, when the outcome is Q, okay, you know that you have to, in fact, to apply this operator on the left and on the right on psi, okay? So which gives you, in fact, the measurement back action, of course. It gives you that the new psi for the qubit is something which is given by this, in fact, two coherent superposition of G and E with this value of the population and relative phase. And here, of course, you normalize. And what you obtain is that the probability to detect your value yk, it is in a small interval, of course, because it is probability density, it is this kind of stuff corresponding to this normalization. Okay, the computation are a little bit more involved, okay, but it is exactly the same rule, okay, as we have done for the qubit. For the qubit, it was, for the photon, it was very easy. In fact, here it is a little bit involved, but the only difference is that here we have an infinite number of outcomes, okay, continuous one. So we have to deal with, in fact, instead of probability, we have to deal with probability density. Okay, but it is the same. Okay, so here I have my operator here in a certain sense, MQ in a certain sense here. Okay. So I will now put this in this formulation, okay? But you will see that in fact the mu is infinite. So I have the density operator formulation is this. So I have this update with yk. It is in the small interval between y and y plus dy with a probability given by this. And what is the measurement operator? It is this operator. Okay? So you see it is exactly this, but mu now and y in this case corresponding have an infinite, is continuous parameter. And now what you can check is that the trace of this one is exactly this, okay? So the probability density, okay? And yes, it is this. And you can check that you have a completely quantum channel. So instead of having a sum, you have an integral, and you can check that when you take the integral of this guy, okay, this thing, okay, so you take the integral with respect to, in fact, y of this guy, or of this guy, of course, it is 1. The integral with respect to y of this guy is 1, okay? You don't care about the mean of a Gaussian, okay? So it's a Gaussian probability. So 1/2, 1/2, and no, it is 1 and 1, and you obtain this. And then what you can do, exactly as we have done for, in fact, for the photon, you can take, when you have this Q&A measurement, okay, of the photon, of qubit energy, here you see, is the qubit energy. You can compute what is the expectation value of V of rho k plus 1 knowing rho k, and you obtain this. So maybe I can do the computation just to explain. So what is the expectation value of V of rho k plus 1 knowing rho k? So it will be an integral. And I assume that rho k plus 1 is this guy here. So it is the square root. So it is dy here, of course. And for the dy, I have to use this formula. So I have G my rho my dag over the trace. Okay, here I have E my rho my dag over the trace. Okay, and I do this, okay, and what I have to multiply, this is the value, okay, I have to multiply by the probability. And what is the probability? The probability here, it is my rho my doc, this is the same trace, my rho my dag, and I have to multiply here by the trace of my rho my dag dy. So you see that this guy, and this guy cancel. So, and what you have to compute is this. Okay. And you have to, you take this. So here, what do you have here? You take this and you put GG on one side, you put EE on the other side. So at the end, what you obtain the product of these two guys. Okay? And take the square root. Okay? And then you obtain what? You obtain, in fact, the value, in fact, of a Gaussian. Because you take the product of this exponential times this exponential, you have exponential of the sum of two squares, you do some computation, and at the end you obtain this thing. Okay? And you see that you have a population on G and on E that factorize, they get outside the integral. Okay, it is just this. Okay. So you see that with this formulation, whatever you choose alpha, non-zero, and you have to do some, sine theta is not zero, otherwise you have ambiguity, of course. Then, in fact, you get conversions either to E or either to G. so up to now, I have used, in fact, the perfect case, okay? No error. So I have to define what is this stochastic matrix. Yeah.
So you again get the bond rule, is it?
Yes, it is the bond rule.
So, and the measurement was Q and D again, is it?
Yes, in this case, it is Q and D with respect to the energy of a qubit.
And so is this a general result that for any Q and D measurements, you always get the bond rule? And you showed these two examples, but is that always true that you?
So I use the bond rule here.
No, I'm saying the eventually.
Yes, the fact that the probability to converge to G or to converge to E is given by the initial population. Right, yeah. Yes, of course, because you have, of course, here this is the Lyapunov function, the super martingale will show you that you converge to a pure state. And now the probability to converge to this pure state is equal to initial population. Because you have a martingale, you have a lot of martingale here.
Yeah, so my question was, is this always true for any like Q and D measurements? I mean, like you showed these two examples where it's...
Yes, I think so. You define Q and D measurements, and it is almost in the definition in this case. Yeah. Yes.
But you're talking about convergence, so I think that means you go k plus 2, k plus 3,
yes,
k
yes.
plus 4.
Yes.
And I guess that means the scenario is that in every interval, there's a re-preparation of the photon state to
Of course.
coherent state, and then a re-measurement of Q. Each
yes.
time,
yes.
repeatedly.
Yes, yes, the same.
Which, of course, is a bit of a schematic representation
yeah.
of the
Yes, it is just to see how, when you reverse the role of a photon and the qubit, use some epsilon, of course, okay, and pass to the limit and see that in the limit you get a stochastic master equation. It is just to play with this thing. But at the end, when you see, even in superconducting circuit, you inject, so to test, in fact, to measure the energy of a qubit, you inject more or less some coherent pulse. You get in scattered things another coherent pulse, okay, another response, and when you measure it, you have two blobs. You see here. One, either you take your coherence pulse, it is here. So if you measure. The trick is this one, it is exactly this. So what you assume that initially in the QP plane, okay, if you take the Wigner representation, you start for the photon, you start with something here, okay, it is E alpha. And then after the things, okay, when you measure, you see that you turn either on this side or on this side. So if you measure something, you obtain or something like this, okay? And the measurement tells you if it is slightly positive or slightly negative, if in fact the qubit is in E or G, okay? It is just here to play with this formula and to see that we do exactly the same computation, okay? But a little bit more involved. So, and what is measurement imperfection? So it is something where, in fact, you can use, so you have Gaussian. So to compute integral, it is nice to have Gaussian, in fact. So you use this thing. So it is exactly here. So what you do, mu becomes Q, the true measurements, I will say, and Y remains Y, and this guy is replaced by exponential of Y minus Q square over 2 sigma. Okay, it is this, yes, over sigma. okay? 1 over the square root of pi sigma. Okay, I use this. So, of course, when you see it is something, you take the integral with respect to q of this guy is 1, okay? And then you multiply and you take the sum. So it gives you a way to do that. My measurement is not very precise. When I get a number, it is, of course, centered around q, but with a small uncertainty given by the square root of sigma, okay? To take into account the fact that your measurement is not very precise, but it is correlated to, in fact, to q. So here you see it is classical probability, and chi, so the partial cross map here is just, in fact, the sum of this guy, okay, nothing else. Okay, and sigma will, in fact, modelize in these settings the imperfection in the measurement apparatus. Okay? And in this case, of course, since I have Gaussian and Gaussian, I can do explicit computation. It is the trick here. And at the end, what you obtain something here where k has this formula. Okay, where it is as if instead, when sigma is equal to 0, so you have a Dirac here. So when you have a Dirac, of course, every coefficient here are 0 except at q. Okay? Then you recover, in fact, the perfect measurement, but here k, so when it is when sigma is equal to 0, then k it is something like this. Okay. And then I applied the Born rule. Okay, the Born rule, I will say the collapse of a wave packet. Okay, and then I do this. In fact, so let's do this first. In fact, in the case of perfect measurements, okay? So I recall, and now I will use some alpha and theta small. So I will first compute the expectation value of y knowing rho. This. And this is something which is minus alpha sigma theta, the trace of sigma z rho. Nothing new. But when I compute the expectation of y square, it is 1/2 plus something which is of order 2 with respect to alpha sine theta. So if I assume that alpha sine theta is a small parameter, what I have, so I have written down this formula in a, I will say, exact formula with hyperbolic cosine and hyperbolic sine, okay? And you do, with respect to epsilon, asymptotic expansion, okay? And what you obtain is this, here. And here it is the probability to detect up to higher order terms, okay, with respect to epsilon y, because y, of course, since y2 is 1/2, okay, well, so you have a standard deviation of this. And what you recognize here, something which is more or less close to, in fact, the stochastic master equation. Here you have the Lindblad term, here you have the measurement back action terms, and here you have something which is the noise. So you can, as usual, when you do these things, you replace epsilon 2 y2 by the expectation value, and you neglect higher order terms. It's not very precise, this. You can put it precise if you want, this convergence. And then what is important is that you put epsilon 2 is something which is proportional to dt in this case. And then what you obtain is the fact that if epsilon 2 is 2 dt, you obtain this thing, so it is a standard computation, and it is as if you have dw and dw square, and here you neglect higher order term with respect to epsilon. So epsilon 2 is dt, so it is you neglect dt square terms. And at the end, when you assume that it is very small, what you have the update of rho. It is this, where in fact dy is something that you get, okay? And dw, okay, so this replace, in fact, dy square, the two rules, and what you obtain is the stochastic master equation. So it is a little bit involved, the computation, but you see there is nothing new, in fact, in this thing. It's a way to pass to the limit, if you want. Okay. So what is important is to understand this machinery here. And then, of course, the devil is in the precise computation, as usual, as usual. So here, I choose all the things to be simple at least, okay? But it is never so simple in practice. Okay. If I have errors, so I have more or less the same thing, but what appears is something which is eta, which is the detection efficiency, and the detection efficiency is related to the sigma here by this formula. And I have exactly the same thing, but you have to take into account this in the formulation. Okay? And now we are ready to do exactly the same computation as we have done. Remember, we have already done this computation, but without all this approximation. It is here. This is the Lyapunov function, okay? That decrease and tend to 0. So what is this guy for the stochastic master equation? It is the product of the population in G times the population in E, and you take the square root. Because it is important to have something which is homogeneous of degree 1 with respect to rho to have this simplification. It is the key issue here, okay? It is something which is homogeneous with respect to 1 with respect to rho. Okay. In this case, you have exactly the same thing. So you agree with me that this guy, it is z, 1 minus z squared. So it is 1 minus z times 1 plus z. Z is equal to 1 is excited state. Z is equal to minus 1, okay, is equal to, in fact, the ground state. And the product, it is something which is proportional to, in fact, the product of the population in E and in Z. And what you have, so you have this here, and what you have to do is, in fact, to compute the expectation value of so in this case, it is how V evolves, so it is the increment of V.
Maybe just a question.
Yes.
You don't use the same Lyapunov function here.
It is exactly the same.
It's exactly the same?
It is exactly the same because of this. So maybe I will explain and take this one. Okay. I will go there. It is the same Lyapunov function. And you can do more or less the same computation, but with Ito rules to have an exponential convergence to 0. So you remember V of rho, what it was? It was the square root of G rho G E rho E. You agree? What is G rho G? With respect to the, in fact, to things. It is 1 plus z over 2. You agree? When z is equal to minus 1, it is, no. No, it is z. It is minus z. Yes. Z is between no. It is, yeah, anyway. So it is, what is the population respect to the Z? Z is the trace of sigma 0. So it is E rho E minus G rho G. So when I have to 1, it is E rho E plus G rho G. So when I take Z plus 1, okay, it is Z plus 1 over 2. And the other one, it is E rho G rho G. It is, alors c'est ça moins ça, donc it is 1 minus Z over 2. Hein? Ah non, ici J. No, it is E. So I don't care. So I assume that sigma Z, it is, I assume that sigma Z, it is EE minus GG. So I don't care what is the first and the second one. Okay, in this case, I have this, so it's just, okay. So you see that when I take the product, I obtain something which is proportional to the square root of 1 minus Z2. Okay? And then you have to do Ito rules for that. Okay. And if you use Ito computation, of course, you have to compute, you know, you have a Ito correction, okay? So you compute dV. So dV is something which is related to dz, but you have to use the second order terms. And in the second order terms, you have this guy. So the dz, when you look at this equation, the dz is 2 eta 1 minus z2 dw. It is just, in fact, proportional to the noise, okay? But with a coefficient that vanished when z is equal to plus 1 or minus 1. So it is clear that this guy gives me in average 0, because I am in the Ito case. dw is independent of z, not Stratonovich, okay? And dz square, it is very easy to see, and you have simplification of this. And you have an exact thing, is that the increment of, in fact, dv is proportional to v. It is an exact solution. Okay, and then you can compute this. Okay, it is a linear equation in expectation value. Yes?
Small typo in this thing, so I'm checking that I follow. In the middle, you have your equation for dy t. I think it's missing an ET factor.
Yes. Exactly. Yes. There remains a dt here. It is here, you see? So it's, thank you, David. Here you miss a dt. No, there is a dt.
No, but I mean
No, in here, yes. Here there is a dt here. Okay. Voilà. So, and now I will explain what is the general structure of, yes, maybe I will. So to summarize what we have in discrete time, we have this. So I will erase this guy. And then I will say you remember I have rho k plus 1. It is k of yk of rho k over the trace and I have the probability that yk is equal to y knowing rho k is equal to the trace. Okay? These are the two things. So everything is here. And we will see that we can formalize. So And now we will do, so I start with a diffusive equation, okay, like this, with different quantum channel, different, in fact, detection efficiency. So I have here, you recognize the Schrödinger equation, here the Lindblad terms, Tt. Here for each decoherence, Lindblad decoherence operator L nu, I have a detection efficiency with the noise depending on nu, and dy is something like this. And I have a detection efficiency which is in factor of these two guys. So first, assume that, as here, that in fact, this guy is independent of y, is just a factor of k. Okay? I have no information in y. Okay? Which means that I have this probability doesn't depend on rho in a certain sense. Okay? It corresponds more or less to what is called to dark state in this case. I have no information. If I have no information, which means that the detection efficiency is 0, what I have here is just the Lindblad equation in a deterministic case. And your measurements is just pure noise, but has nothing to do with the system. So you can throw out your measurement. It is completely out. And to all what you can do is this. So this is the, I will say, a continuous time quantum channel. Lindblad master equation is nothing but a continuous time quantum channel. Okay, this thing. So what is nice is that I can, with Ito rules, write this equation like this. It is exactly like here, but in this sense. So I have a partial cross map here, a cross map, you see, where in fact the M depends on the measurement outcome here. And I divide by the trace, okay? And what is, in fact, this measurement, this M, this Krauss operator, it is this thing. So here, it is identity. You have this operator times dt, and here you have L nu times this thing, okay? And then I divide by the trace, and I will show you, not in general, but on a specific case, that writing this, or writing this, it is exactly the same things when you use Ito computation. But it seems to me that this formulation is much more appealing than this one. Because of two things. The first thing is that you see directly the probability of detection of dy. And here what you have, the probability of detection of dy, it is something like this. You have the Gaussian, but the Gaussian is not shift, as usual when you see. People say it is a probability that is shifted. No, no. It is independent of rho. The dependence on rho is on this part, and when you look at the dependence with respect to y, it is a polynomial of degree 2, which is always positive. So the probability to detect y is something which has this formula. And it is important to have this. Which is a linear function of rho. So in a certain sense, in this, what you have, so I will take only one, so I will take h equals 0 and only one L in this case. Here it's just the general formula. So what I have is, you agree, I have d rho of t. What it is d rho of t? It is rho of t plus dt minus rho of t. And it is, if I write the first equation, it is L rho L dag minus L dag L rho plus rho L dag L over 2 dt plus, So I will take eta is equal to 1, okay, in this case, to see that it is exactly the same thing. Plus, in fact, I have L rho plus rho L dag minus the trace of L rho plus rho L dag, rho. And what is dW? dW, it is dy minus the trace of L rho plus rho L dag dt. Okay? And dy of t is equal to the trace of L rho plus rho L dag dt. And in this case, what is m? M of dy, it is 1 minus L dag L over 2 dt plus dy L. Okay? And my update, in this case, eta is equal to 1. It is, so I have this. And what I want to see, it was written this or written this in the Ito sense. Rho of t plus dt is equal to m dy of t, dy, rho m dy over the trace. And the probability to detect dy, knowing rho, so in the square root of dt, s plus ds, okay? Dy in knowing rho. And it is something, okay, which is proportional to ds. Here I have exponential of minus s, so I have normalized. So it is minus s2 over 2, the square root of 2 pi. I guess it is this, yes. And then in front of it, I put the trace. So you see that in this case, m is an affine function of dy, okay? So this trace here is a polynomial of degree 2 with respect to dy, and it is always positive. So in a certain sense, the probability given to get dy is not exactly the Gaussian, but it is a Gaussian with, in fact, a polynomial, which is a plus bs plus cs2, okay, where a is close to 1. Okay? It is something like this. So it is a very good, yes? This one. Yes. In this case, when people say, well, in fact, the probability to take dy, what it is in fact a Gaussian, but which is slightly shifted by this value. So it depends non-linearly on rho. But if you use Ito computation, it is as if you use linearity with respect to rho. The non-linearity is just, in fact, something that appears in the limit, but it is not important, this non-linearity. So, and I guess that this formula is, in fact, something much, and for this. And what you can do from this analogy here, you can get, and I will show you the small modification to this scheme, to get a numerical method, okay, which is based on completely positive recurrence and also trace preserving. So let's go there. It is a CPTP numerical scheme for diffusion SME. Okay, so you have this, and all what you have to, yes, first, before, it is a very good exercise to prove with this, okay, with Ito rules. With Ito rules, what you have with Ito rules? and use the fact that dy square is equal to dt with Ito rules. So you take this, okay? You use Ito rules with this guy, with this thing. You don't care about what is dw, okay? And you know that dy is of order the square root of dt. So use this, and you obtain exactly this. It is a very good exercise. It is as if, okay? It is just an exercise with Ito rules to prove that this is exactly this when you use Ito rules, noticing that dy square is equal to dt, and you obtain exactly this. Okay. I'm not sure that I have time to. But you know, I do not have time to do this. So try to do this, maybe if you. Now it is the way. Let's start first, maybe. So I will erase this now. And even for simulation of Lindblad master equation. Let's use d rho over dt, first thing. Just one term. L rho L dag minus L dag L rho plus rho L dag L over 2. You want to integrate this differential equation. You know that the propagator of this equation is L of rho, and you know that application to rho, which exponential of t L of rho is a completely positive trace preserving map. You know this, okay? And what you want to have is to have, you take a small dt, and what you want to have at t plus dt is equal to a quantum channel, of course, depending on dt of rho of t. And you want to have k of dt a quantum channel. Okay? To do this, the trick is this. Of course, you assume that dt is small. You use this formulation here, but you modify it slightly. So what was M0 at the beginning? So I know that I have k of dt of rho. It is something which is M0 rho, M0 dag, plus, in fact, here I have dt L rho L dag. If I use this. Okay, eta is equal to 0. I have only one term. So here, dy here. So it is as if I have no. So I have only this term. With M0 is equal to 1 minus L dag L over 2 dt. Okay? It is this. So this numerical scheme is known, of course. So I don't remember, it is a colleague in Canada, I guess. But it is not trace preserving. Yes? No, it is this. For this. What do you mean? Over 2 here. You agree, when I do this, you agree that I have k of dt rho. It is 1 minus dt L dag L over 2 rho, 1 minus dt L dag L over 2 plus dt L rho L dag. So you see that it is 1, okay, plus dt L of rho, which is here, okay? But you have second order terms. And it is plus dt square over 2, I have L dag L rho, L dag L over core. Okay? And of course, when you compute the trace, it is not exactly 1. So people say, well, I do this and then I normalize. Okay, but it is a nonlinear scheme with respect to rho. To avoid this renormalization, replace M rho by what is here, okay, M0, and you multiplied by, in fact, S. What is S? The big S, in this case, it is 1 over the square root of M0 dag M0 plus dt L dag L. And, okay, and L, you replace it by L factorized times this, the inverse of this thing. And this is M0 tilde, this is L tilde. So when you see what's, c'est ça? So in this case, what you see is that, in fact, you have a modification of your numerical scheme. Okay. But in this case, il me semble que c'est pas bon. Is it this exactly? So I will continue the computation there. And in this case, what you get, so I get M0 tilde rho, M0 tilde dag, plus L tilde rho, L tilde dag, okay, dt. I want to compute the trace of this guy. What it is the trace of M0, okay, over 1 over the square root of S, rho. Here I have 1 over the square root of S, M0 tilde, plus L, 1 over the square root, rho, 1 over the square root of L dag, dt. I put everything, okay, on the other side, so it is the trace. Okay, so this is of M0 dag M0. Okay. Here I have 1 over the square root of S. Here I have 1 over the square root of S, rho, plus dt, 1 over the square root of S, dt L dag L, 1 over the square root of S, rho. And when I take the sum of this guy, it is equal to the trace of 1 over the square root of S, S, 1 over the square root of S, rho. So it is 1. Okay? So this way, what you obtain up to higher order modification, you obtain a numerical scheme which is exactly equivalent to the earlier scheme, okay? But up to higher order terms, that gives you an exact quantum channel. And the second point is that, and typically it is important for bosonic code, when you take L is equal to A, or A dag, or I will say N, you have unbounded operator, but for a quantum channel, this operator should be bounded. By the division by the square root of S, you obtain always bounded operators, which gives you something which is very interesting for simulation of infinite dimensional system when you take truncation, Galerkin approximation and truncation this. Okay? You do not need, in fact, to use a very small dt if the population where you truncated is small. Otherwise, you may have some troubles, instability. Okay, so this numerical scheme is interesting. Of course, not for simulation of a qubit, I will say. Not so sure, because you can take a dt quite large with respect to over dt. But for, in fact, infinite dimensional system, like bosonic things, and it is interesting to use this kind of things. Okay. So it is diffusive equation. So jump equation. You can do exactly the same thing. But in this case, so just to see, what we will do is I will assume that I have vacuum in the photon. Psi is the state of the qubit. And here I assume here that I have, in fact, a resonant interaction. So I can exchange things. So when you applied this operator on this thing, you obtain this thing. So of course, since you have only one excitation in G, you have only one here, nothing else, okay? And you measure, in this case, so your measurement apparatus is the number of photon number, okay? This is what you measure. So when you measure your system, the state of a photon, it interacts resonantly with a qubit. So it is either, in fact, in population 0 or in population 1 with this probability here, okay? So what you obtain is just here you have a M0, M1, okay, where M0, it is this operator here, and M1, it is this operator. So nothing, no, the computation are much more simpler here because I have only a discrete number of a value for the output. Okay, it is only two possibilities. So I guess that they miss a minus here. Okay, yes, there is a typo here. You have a minus here. So you have a cross operator like this, then you can compute what is the, of course, you send the photon in vacuum. You have resonant interaction with a qubit. So what you can, from time to time, if you detect one, you have remove one quantum of excitation in the qubit, so you have to be in 0, okay? In this scheme, when you detect one, you know what is exactly the state of a qubit, okay? If you detect one, you have projected on G. Okay. No, it is positive, no. So what you need is that this cosine should be not 1, which means that you need that the sine should be not 0, okay? Just this. So no, it's okay. It's okay. So you can do this, and you can prove that you converge always to E. You detect 0, 0, 0, don't know, but once you detect one click, it is a excitation of a photon, of a qubit, and you measure the photon, the fluorescence photon. It is exactly this. So you cannot imagine something simpler in fact, in this case. Okay. No, it's not Grandy. You converge to 0. So you have an environment which is in vacuum. It exchanges energy with your system, and the system, in fact, goes to its ground state. It is okay, as usual here. It is the simplest situation. So your system is a two-level system. Your environment is an oscillator. The oscillator is in ground state. Okay, and you say, I have this interaction. I measure one photon in the environment, so I know that my system is in ground state. Okay, so it is a way of. It's nothing more here. It's something. Okay, and now jump SME. So in this case, what we will assume is that theta is small. Just this. If you assume that theta is small, you take what is the probability, in fact, to get 0. Okay, so no jump. Okay, in a certain sense, and the probability to get 1. Okay. And when, in fact, sinus theta is small, okay, the probability to detect 0 is almost 1, and the probability to detect, in fact, one photon is small. Then the scaling is now very similar. So you say that sine square of theta is dt, and y is dn, okay, is your counter. It is either 0, or it is you have one click, okay? And you can write down, in fact, the expectation value. So what is the average value of dn? It is, in fact, this probability, and this probability, it is typically this trace here. So you can write down, in this case, with dt, what I have written before, exactly as this one here, which means that you have your Lindblad equation with L is sigma minus this excitation, okay, of a qubit. Okay, it is the T1, I'll say to T1 of a qubit. And here, what you have the fact that either dn is equal to 0, okay? If dn is equal to 0, you do this, you have a nonlinear differential equation. When dn is equal to 0, you have an evolution which is nonlinear respect to rho, it is as usual, and which could read like this. And when dn is equal to 1, of course, d rho should be, so it is a dn, d rho, when you have to apply, the rho is equal to this, okay, with this probability. Okay. And m1 is the square root of sigma minus. Okay, in this case. Yeah.
So is it correct in this setting, when I see square root of dt, I have to think of that as a deterministic infinitesimal and not sort of be sleepy and say, oh, it's dw, which would be a stochastic infinitesimal.
Here.
At the very bottom, you have square root dt. And I'm trying to assure myself that no, that's not dw.
No. It's just to put it like this. Here you have a dt. It's just this. Yes. It is, the square root comes from the fact that I have a sine square. You see, the square root comes from this. In m, I have a sine here, and I take dt is a sine square. So it's just this.
There's never any role for the
No. And in the previous formulation, the fact that you have Wiener comes from the Gaussian, and the Gaussian comes from coherent state. It is very different. Okay? But you can treat it as a Wiener process, of course, when it is very small. So. Voilà. Yeah. And you can do exactly the same thing. So it is for this. So if now you assume that we have not a perfect detector. So you have two kinds of problems with counter. You have dark counts. You have a click which has nothing to do with your system. It is dark counts, click from time to time, with a certain rate. The rate of dark counts is theta bar here. It is something which is positive. You have a certain rate of dark counts. And you have also detection efficiencies, which means that you have a true click, but you don't click. It is eta bar. If you want, in fact, to take this into account in your Poisson in the formulation, here, what you have used this stochastic matrix. It is a left stochastic matrix. Here you have M0, M1, and here you have, in fact, the fact that you detect no click or you detect one click and do exactly the same thing. So what you obtain is this. You see, it is, I take no click, I take here, I have M0 and M1 here. So I take -1 minus theta bar dt times M0 rho M0 dag, plus this coefficient times M1 rho N1 dag, okay? And divide by the trace and so on, okay? And in this case, you have the probability something like this, plus higher order terms. And if you detect a click, you take this part here, which gives you this. And the probability is something where the sum up to higher order term is 1, okay? The sum of 2. Okay. And if you write down in fact, as usual with a Poisson process, what you obtain, you have to change here. Okay, instead of having when theta bar is equal to 0 and eta is 1, you recover the previous formulation. But here you take into account dark count and detection efficiency, and you have here your update. Okay. And from this, of course, it is when dt is very small. So you have neglected higher order term in dt. So which means that if I take typically the trace of this guy and the trace of this guy times dt, it is not exactly, the sum is not exactly, in fact, the sum is 1, but it is, okay. But you see, assume here that theta bar is very large, okay? And you choose a bad dt. You may have something which is here, which is negative, okay? So you want to preserve, in a certain sense, positivity of a probability. In this case, the trick, so, yes, this is the general formulation here. When you put an H, you put a V, and so on. So this is exactly the same thing. And this formulation, it is, since a long time, it has been, so here is a paper of Jean Dalibard, Yvan Castin, and Klaus Molmer, 30 years ago. You have also the same thing, more or less, with Peter Zoller, it seems. At the same time, they were on this. It was used, this kind of Monte Carlo simulation, to simulate, in fact, stochastic master, want to solve master equation with rho of large dimension, and they use, in fact, the wave function simulation, wave function, so they do not use this. Theta bar is 0, and eta is 1, and they use this by doing Monte Carlo simulation to get some information on what is rho, this large dimensional stochastic master equation. It was for numerical computation, this. But in fact, behind this, you have this thing. And then I will conclude by completely positivity and trace preserving numerical scheme. So it is this. You do exactly the same thing. The M0 and here the L. So the normalization is the same because the normalization is valid only for the Lindblad equations. You only take this. And then what you do is something like this. If you want to take any dt, any theta bar positive, okay, and any eta between 0 and 1, you have something which is, in fact, an exact formulation, in fact, what we have. So when you take this guy plus this guy, it is an exact quantum channel, okay? and the probability which is here plus the probability which is here, it is exactly 1. Of course, assume that theta bar is large. Okay, you have something, you replace 1 minus theta bar dt by exponential minus theta bar dt. Okay. So it is a numerical scheme that you can use even for dt quite large with respect to your system. The last point, of course, if in general what you have, H, so the transition probability, the transition between the, so in the spectra, okay, of H in general, the frequency in H, in general, they are larger than, in fact, the decoherence and the measurement in general. In this case, you can use some splitting scheme. First, start, you take dt, okay, splitting is this. To finish with, in fact, so if you have this, where in a certain sense H, I will say, it's much larger than L dag L, okay? Something like this, okay? So then in this case, to do simulation, you can split in. You choose dt, and in this splitting scheme, you assume that you have u, which is exponential of minus e dth over 2, and you can compute this with good precision. Is okay. In this case, what you do rho of t plus dt. So you first start by exponentials of u rho u dag at t. So it is stat f. Here you put what I say. Here I put exponential u dag here. And here I put my k of dt, u dag, where k of dt my exact quantum channel, it is this. M0 tilde rho, M0 tilde dag plus dt L tilde rho L tilde dag. Okay. So you split. You first half time step to use, in fact, Schrödinger. Then you use decoherence, and then you use this. In this case, you have a completely trace-preserving okay, map, which is it is a numerical trick. Okay, but you need to have a good approximation of this guy. Otherwise, if H dominates, you have to use a small time step. Okay. Yes, in M0 and M0 tilde, it is 1 minus dt L dag L over 2, of course. It is the evolution here, okay, without the Hamiltonian. Okay, it is a way. And it is quite useful typically for infinite dimensional system, this kind of stuff. Yeah. Yes. Yes, you can use even for the yes you can use in general the dt you can take it quite, I will say, large, which means in a certain sense dt times this guy around 1/10. typically.
If that condition is much greater than LDAR.
No, just to say that the splitting could be interesting here, because if you want, if you have typically, if you want to simulate your system without using the rotating wave approximation to see what are the correction and so on. In this case, you need very tiny, in fact, time step to follow the high frequency. If high frequency, you know how this exactly, instead of having a lot of time step for one period, you need maybe 10 time step per period, and it is enough to have a good precision. You don't need to have 100 time step per period. Okay. So you gain here. It is at least my experience on this. To use this scheme. So it is a numerical analysis, but to do simulation, you have to be aware of this to avoid spending too many times in simulations at the end. Okay. Well, that's the end of this lecture. So I am a little bit. Oh, it's okay. So if you have other questions, so thank you.
Thank you. Is there some questions on today's lecture or past lecture?
One question. So, I mean, so you discussed mostly H equal to 0 case, where at long times the eventual state is quite simple. It always goes to the ground state.
Yes, yes, in this case.
But if you have H, then in general, what is known, I guess it becomes much more complicated, right?
Yes, of course, in this case. So if you have assume here that take this, and instead of putting 0, I will say take thermal state, for example, or coherent state. So the investigation of this thing is not so simple. And in particular, where in fact the sign of theta square root of n vanished at certain value. You see? Okay, in this case, you have what is called the phenomena of trapping state, and the asymptotic regime is not so simple because you have trapping region in this case. So of course, if you put here a coherent state and want to analyze in fact, the convergence with respect to the value of theta, it should depend on the fact that theta over pi is close or not close to a rational number. Okay, so it should be, so it is an interesting problem, I guess, to characterize the asymptotic regime in this case. I know. It is because here I have 0 that I have this in this case. So it is something, but we have looked at it during the thesis of Zaki Lektas, but it was difficult things because of that. Okay. But it is, I guess it is an interesting problem. Wow.
Is there other questions?
Yeah. Yes. Assume that you test. Yes, it's a very good question. I agree with you. Assume, maybe I never ask this question here. Yeah, it's a very good question. Assume here that I have a Schrödinger cat. What's going on, I don't know. Maybe. Yes, if you put a Schrödinger cat, so you should get, because you still have Gaussian in the process. But if you take, for example, I don't know, GKP state here. What's going on if you take a GKP state? Don't know in this case. So I think that the conclusion of these two lectures is that this experiment that has been conducted in Paris, in fact, it finished more or less this kind of experiment 10 years ago. And it is a very good, in fact, setting, which is, in fact, close to some experimental realization, okay, but which is very interesting to explain the rule of quantum mechanics and how from these basic rules we derive, in fact, equation, which are the stochastic master equation in discrete time or continuous time. They have exactly the same structure, okay? And that can be used by all the community. Either you are a control engineer or an experimental physicist to do something. So it is something which is, if I take a parallel what's going on in automatic control, it replaces, in fact, the Kalman formulation of system, okay? In a certain sense. In control engineering, I guess that this stochastic master equation can play an important role, in fact, to design, in fact, a quantum system, to control them, to calibrate them, and so on. Because calibration comes from the fact that in this formulation here, so everything is here, is that you have a probability depends on parameter and so on, so you can do a lot of things with this. If you have a model, of course.
Is there another question? I may have one actually, that in your technique using this M tilde and L tilde, I guess that the difficulty is to compute this inverse of the square root of the operator, because this may be a time-consuming operation, right?
This is for numerical scheme.
Yeah, but this, like this part in the numerical scheme.
Yes, but when you see S is always positive.
Okay. It's self-adjoint, and so it
is self-adjoint.
Yeah, so it should be
so
easy.
you can use typically the LU decomposition, and you don't need the square root. If you put an L on one side and the LDAG on the other side. So you use this, and use S is equal to LLDAG. This is more or less the square root you put on one side and the other side, you have exactly the same. So take a big matrix, positive, Hermitian, okay? What is the LLDAG decomposition? It is something that you have very efficient routines for that, even for large matrices.
Okay. If there is no other questions, but I guess you can discuss also at the coffee break or tea break. So we have a tea break now, and we reconvene at 11:30.